Okay, so thank you very much. I've turned on the technology, hopefully it's working. So thanks all very much for coming. I know we've got a competing attraction in the main lecture theatre, so in fact I'm actually directly clashing with my own postdoc this morning. I said she'd get a bigger audience tonight, it would. Anyway, so thanks for being here. So you've got my title there, so I'm going to try and tell you a little bit about some work we've been doing on what I think is quite an interesting coupled free boundary fluid structure interaction problem. But before I do that, Uwe asked me to kind of start with a bit of a more general introduction to kind of introduce myself and some of the things I've been doing. So I hope he meant that, because that's my first few slides are a little bit more general. So what I'm actually going to do is 2 minutes just give you a flavour of some of the things we've done, really with the hope that it'll spark a connection in your head or something that you think of that you want to talk to me about later. And then maybe 10 minutes just talking quickly, just some pictures really, about 4 problems we've been doing currently or recently. And again, just to give you a flavour and to make some connections, because I've already, I've been here a couple of weeks and I've already talked to a few people about some problems related to these things, but I'm sure there are other connections there that I don't want to miss out on. So 10 minutes maybe just saying a few words about some things we've been doing, and then the main talk around about 30 minutes, and that adds up to significantly less than 60, which was also the brief I was given, so I was told to leave plenty of time for discussion at the end, so I will try and do that. Okay, so let's start with the more general stuff first, some brief highlights. So I guess just where I'm coming from, my original background is as a mathematician, but I've always been interested in solving real world problems, and here's a few examples of the kind of problems we've worked on over the years. So first of all, I have to credit my long-standing collaborator and great friend Brian Duffy. Some of you will know, many more of you should know, who's been involved in many of these projects and is a fantastic guy to work with, and without his contribution a lot of this stuff just wouldn't have happened. So one of the collaborations we've had with him has been on a whole variety of thin film flow problems, rivulet sheets and such like, and I'll briefly touch on a couple of those later. And one particular project I want to mention is work on droplet evaporation we have done and are doing with Khalil Sefian, who's an engineer based in Edinburgh. And that's really been a great project because he's an experimentalist and he's produced all sorts of fantastic data for us to come up with mathematical models for. So I'll briefly touch on that a little bit later. A few years back, I spent a bit of time at Northwestern, and what I did there was work on some nuclear boiling problems. So that's quite a fun problem, phase change, bubbles, and related phenomena, and that led on to a project with David Kenning, who was in engineering in Oxford, where again we tied up some nice mathematical models, some mathematical models that seemed to work with his experimental observations. He was doing kind of explosive, he created bubbles, vapor bubbles in small capillaries explosively that blasted out of the end of the tube, sometimes broke the tubes, but this explosive bubble growth was quite an interesting thing to model. And it kind of came out of the...
When you were at Northwestern, were you in the mathematics department or engineering department?
Both, neither, because Northwestern have an engineering math department. So there's a math department, and there's all the normal engineering departments. Steve Davis and some of the other people you might have heard of are actually there's a separate engineering mathematics department, and that's where I was, which is great. Because it's actually based in the same big building as all the engineering and physics departments, so you could go to engineering, physics, chemical engineering seminars without going out into the cold. I did go to the math building twice, one occasion to borrow a book, which I didn't really understand, and the second occasion to take the book back. So I'm afraid it was very much the engineers that I was there to deal with, not the mathematicians. That's pretty unusual, of course. It's pretty unusual in Britain as well. There aren't many engineering math. I think there's probably only one engineering math department left. But anyway.
This is unique really in Northwestern.
Is it? Yeah, it must be pretty close to being unique. So it's almost unique in Britain as well. Bristol is the place in Britain that still has a separate engineering math department. It's very good. So, as I say, just briefly, I don't want to take too long, interest in liquid crystals, which I kind of dabbled with, and some of you in that area will know Nigel Mottram and other people at Strathclyde. Strathclyde's always had a very strong tradition in liquid crystals, and that's why I'm very delighted to be here for this month, because it overlaps with the other programme on liquid crystals, of course, which several of us are involved with. And Dave Pritchard, who you may not come across yet, but you'll certainly will have done, a very good young scientist who spent a bit of time in Cambridge before he came up to us in Strathclyde, and he's got an interest in non-Newtonian flows, geophysical flows, and we've done some nice interesting stuff with him I'll mention briefly in a moment or two. And we currently have a project with Nottingham Trent, and I'm going to not have time to talk about that, and that's what Lindsay Coulson, my postdoc's talking about as we speak in the other room. But that's a liquid crystal project to do with electrophoresis. Spent a little bit of time with Howard Stone last year. Absolutely brilliant. What a fantastic guy. What a fantastic group. That was a real pleasure. And a little bit of time in Oxford last year as well. Okay, and there's a journal you may have heard of. So, look, we'll spend a few minutes talking about some current problems we're doing and then move on to the main feature, so to speak. So, I've got 4 problems, a few slides on each one. Hopefully there'll be something of interest in one or two of them for you. So, here's some stuff we've just been doing about pinning, depinning and repinning of rivulets. And as always, must credit the guys who did all the work. Brian Duffy, I've mentioned to already. The student who's finishing up his thesis in Glasgow as I speak, Colin Patterson, who did all the heavy lifting on this one. And there's a paper that's about to appear. So the problem we were interested in was this one, where you have a horizontal cylinder and you're dribbling fluid over it in some way. And so here's, for example, if you're supplying fluid from the top and it drains round to the side. You're interested in all sorts of things about that problem, but one thing you might be interested in is the shape, the configuration of a steady flow. Can the flow make it all the way around the cylinder, or is something else going to happen? And here's, if you look at a very simple, steady, thin film theory, you can very easily get a very simple prediction out that says that a large cylinder, a slowly varying rivulet, all the kind of obvious simplifying approximations you might make, that if the rivulet starts off being sufficiently narrow, there's a critical width you can calculate, then indeed the rivulet can make it all the way around to the cylinder and drop off the bottom. But if you make it a bit too wide, then you find that it can't do that. You can flow around the cylinder at a certain angle here, alpha crit in this notation here, and then the solution just can't continue. Various possibilities. It could be unsteady, it could fall off, but one other possibility, the one we followed up, was that instead of having the pinned contact lines, which is what I've tried to show there on the sketch, is the contact lines can depin, and you can end up with the rivulet pulling in, detaching, depinning, de-wetting, and still making it to the bottom of the cylinder, but with a narrower width, with a different shape. Okay, so that's a very simple undergraduate little calculation you can do. So one thing you can do with that kind of solution once you've got it is say, well, that's great, but of course real contact lines don't stay pinned until the contact angle reaches 0, and other possibilities can occur. So one thing you might be interested in is if you had a rivulet with variable width, and that pinned at a particular critical width. So this is a rivulet. Not the one I showed you on the previous slide essentially had fixed width, apart from when it depinned at the bottom. So another alternative situation is where you have a rivulet with fixed angle but variable width, and that's what I've tried to draw here. So it's a rather it taxes our three-dimensional drawing skills to draw these, but here's the fluid going around the cylinder. It starts off being rather wide and gets narrower towards the middle and eventually falls off at the bottom. So that's certainly one possibility, but other possibilities are, for example, that you might get to a critical width, a critical width of the rivulet here where it pins, where the contact lines become fixed, and then there might be a region in the middle where the contact lines are pinned for a while before depinning. You can indeed have a situation like this where you get depinning and the contact angle goes to 0. So there's a variety of possibilities. I'm not going to go through them all here, but once you have this idea of the basic rivulet flow, you can work through exploring all of these possibilities and come up with some rather nice pictures that tell you, for you can calculate how the width the angle and the height vary with, for example, in this case, as you vary the contact angle. And so here we've got a situation where the width is decreasing and then hitting a minimum here, hitting a floor here, where the contact lines get pinned. So here's a situation where you get a variable width rivulet being pinned and then depinning. That's why I've called it pinning and depinning. And it depends whether, it depends on the width, it depends on whether you're pinning bigger or less than the critical value. It turns out to be pi in this case, and you get the same kind of pictures with the sort of different details. So that's one possibility. A second possibility is a bit like the one I started off with, where you've got a rivulet with a prescribed width. Can that make it all the way around the cylinder? Well, as we've seen already, maybe it can't. And so you could have a situation where you have a fixed width rivulet, where you have one that has to depin at some portion. In this case, it's pinned, it depins, and then it repins. Or indeed, maybe it isn't allowed to repin, maybe it depins and then flows all the way to the bottom of the cylinder. So again, another possibility, another set of possibilities you can work through. And here, for example, now we've got the contact angle, which is varying, hits a minimum, it pins at a fixed angle. So it's got variable angle, fixed angle, and variable angle again. So it depins and then repins. So look at it in terms of the width. The width is fixed, the width is variable, and the width might be fixed again. So that's depinning and potential repinning.
Stephen, can I ask, so
Sure.
by pinning you mean it just stays at the same width?
Yes.
So what's making it do that?
Okay, so it's either going to depin because it depends on what you can think about in terms of the width or the angle, depending on which problem you're doing. So the simplest one, the most obvious one to understand, is where you just hit a minimum, a retreating angle, or a maximum advancing angle. So it could be depinning because the angle has reached a critical value.
Yeah.
So that's what's happening in this scenario here, where you're hitting a critical angle.
So you put that into your
Yes, in this
calculations.
simple model, that's
Yeah.
just something you're feeding in.
Yeah.
So I'm not doing absolutely. There's a whole variety of interesting problems to do in terms of why contact line depins and how it depins, which I'm completely skirting over in this. So, but however, your question was another way it could be depinning is if the width reaches a critical width. Okay, so that's a little bit more artificial, but you could certainly imagine a scenario where the substrate is made of two different materials, or for example, what they can do in the experiments is they can just put a groove on the substrate, mark it, which will pin the contact line. So that's a little bit more artificial, but you can certainly imagine experiments where you could do that. Sorry, I should have made that a bit clear. Okay, I'm going to try and move fairly quickly through this because I'm conscious I don't want to run over my time. So just maybe briefly draw a couple of pictures that we tell you a little bit about some work we did on fluid rings. This was with another PhD student, Adam Leslie. So the problem we were interested in there was if you had a cylinder where you had a ring of fluid going all the way around it. So it looks a little bit like the problem I was just doing. This is something that happens all over the place. There are all sorts of nice experimental results out there for people doing things on This is a rotating cylinder, sorry, I should have said that, on a rotating cylinder. And it is certainly quite possible that you can get a situation where you have a continuous ring of fluid going all the way around the cylinder. So we've got fluid here, we've got dry cylinder here, and what we're interested in working out, of course, is the shape, the size, the width, the height, the weight. We want to know, does it exist? Can it exist? If it does exist, what size and shape is it? Some of you who thought about these kind of things before will know there's a very famous problem in two-dimensional coating flow, first studied by Moffat, of this parish, of course, and many other people since, where he looked at a two-dimensional version of this problem. So you just had a rotating cylinder with a thin film, and he asked the very simple question, how much fluid can you keep on a rotating cylinder by rotating it? And that's a problem you can answer in various ways, but you can answer with a nice simple thin film theory calculation that turns out to be remarkably good. So you could think of this as the three-dimensional version of that problem. Okay, so I'm not going to go write any equations up, I'm just going to show you some pictures. So it gets a bit hard for me to draw this three-dimensional object here, so it's easier to just take this and unwrap it, plotting it from 0 to 2 pi as you go around the cylinder, and that's what's on this next slide. So these are just some kinds of typical examples of the shapes of these rings. So here, at low flux, at low speed, low rotation speed, you get a sort of a long, thin, kind of pencil-like rivulet that just goes right around the cylinder like that. And as you go to higher speeds, more interesting things start to happen. So these are all non-dimensionalized numbers, of course. At higher rotation speeds, you get rivulet shapes that are much more exaggerated. They get deeper on the bottom, they get wider on the top. And the critical solution, the maximal solution, the one with most weight, the one that the most weight you can support in this way has a corner, has a sort of a corner in it here. You can just about see that in the larger of those pictures. These are all things you can work through. You can do all the details of this, and you can come up with a pretty good understanding about what kind of these solutions, when they can exist, how they exist, and what they look like.
I'm sorry, I'm not sure if I understand these pictures. Because your angle is this axis, right? So the theta is the angle. Right?
Yes, so this is the angle around the cylinder.
So the ring.
So yes, there's a danger. There's always a danger with this problem that the different people use different notations. So the way I've set it up here is the theta. Sorry, the theta, the angle, the azimuthal angle, is measured from 0 at the horizontal on the right-hand side, from the horizontal on the rising side of the cylinder. So if you go back to my next picture, that's here. So that's where the ring gets widest. So that you'd expect the fluid to be fattest, where there's the greatest, where the fluid, the rotation of the cylinder is dragging it up, but gravity is pulling it down. That's on the right-hand side. That's near theta is equal to 0. That's where there's most competition. That's where the flow is going to be slowest, and that's where the ring's going to be fattest. So it's fattest on the right-hand side, and it's thinnest on the left-hand side. But yes, you're right. You have to think just to make sure you've got the coordinates all pointing the right way around.
Do you know the stability of?
No. So there's a whole. I could give a whole talk on this, which I'm not going to do, thank goodness. But just there's a lot of work, as you know yourself, on the two-dimensional problem and three-dimensional perturbations to it. We haven't. This is the first time, as far as we know, anyone's done these three-dimensional ring solutions. But one of the things, there are various things you need to do next with this problem. Look at discontinuous solutions with jumps in them, which people have done a lot in the 2D case, and of course do the stability analysis of these things. I don't know, but it's a completely open question. Okay, but again, just very quickly, because I don't want to, I'm conscious I'm already slightly behind my schedule. So just the other interest, we've talked a bit about rivulets, dry patches. Don't go away with the idea it's all steady. As many people in this room know better than I do, that you get, for a thin film flowing down an inclined plane, you get these kind of PDEs for the film height, with the parameters there having the usual and obvious meanings. And sometimes if things are on your side, you can find nice solutions of those equations. We have some experts in the room who know how to do this rather well. We played around with these a little bit, and we found some nice similarity solutions for unsteady rivulets and dry patches. There's been a lot of work before on steady versions of these equations, but a bit rather less on the unsteady version, so I'm not going to try and do any detail. But here, for example, and I apologize for not quite explaining things properly, here, for example, is a nose of a rivulet of fluid that's piling up against an obstruction. So maybe the next one looks a bit more convincing. So here's a rivulet of fluid. We're starting out, for reasons that now elude me. Oh yes, it made sense to start out at negative time. At time t is 0, the thing blows up. So what you've got here is you've got fluid draining down the slope, piling up against an obstruction, getting wider and deeper, all described by this nice little similarity solution. There are other problems like that you can do. In particular, the reference I had on that first slide was for a hole in a sheet that was closing up, and you can do the same kind of analysis. Very finally, just before we get on to the main event, I mentioned briefly thixotropic fluids. I want to say a word or two about that, because I think there might be some connection with some of the people in this room who would be interested in that. This was joint work with Katrina McArdle, who's just submitted her thesis and is waiting her viva as we speak, and David Pritchard, who I mentioned to you a little bit earlier. And just to have one slide on this. So a thixotropic fluid is one that has a structure that evolves in time, a structure that can recover. So the classic example would be, some sort of food stuff that you start to stir it, it's rather stiff. Once you've stirred it for a bit, it goes much runnier, and you put it back in the cupboard, come back 2 days later, and it's gotten stiff again. That's be the kind of classic signature for a thixotropic fluid. The simplest way you might measure that, model that mathematically, is with some kind of structure parameter that reflects the amount of structure there that can be broken down and built up. And so, as well as the usual kind of equations we're familiar with, you'd need to write down some sort of evolution equation for the structure parameter. Now there's a lot of people out there interested in these fluids. There's also a lot of models out there. So what we wanted to try and do was take a fairly simple generic model. This is probably the most generic model of that kind that's due to Muse and Wagner, and try and really understand what that model does in a really simple problem. So we took the simplest problem we could think of, which was just the Stokes problem, where you have a half space of fluid with an oscillating plate, and went through working out in some detail what the properties of the solution were. And it turned out to be surprisingly complicated. I was amazed how complicated it turned out to be. And it also turns out to be remarkably dependent on the parameters in this constitutive law. Because various people, in this evolution equation, people have used versions of this before and been rather careless about the parameters, or at least not worried too much, or kind of assumed that it wasn't really going to make much difference. But it turns out that these exponents in that evolution equation make a huge difference and change the behaviour completely. So there are all sorts of interesting regimes, fast, slow, and pseudo-Newtonian behaviour, and a whole lot more interesting, a lot more in that than we expected. So the take-home message from that was, even a really simple problem for one of these isotropic fluids turns out to be surprisingly complicated. So goodness knows what happens when you start to do complicated problems. Because if it took us 2 years to understand the Stokes problem, what about more complicated problems? There's a heck of a lot more to do. Okay, there's a few other things we're doing, but I don't want to spend time on that now. If any of the words on this screen are of interest to you, then please do come and talk to me. I'm here for the next couple of weeks. Okay, so I didn't quite stick to my schedule, but I'm still confident I'm going to finish ahead of time. So that what I'd really like to tell you about today is spend the next 20 minutes, half hour, telling you a bit about that floating plates problem that was in the template. Okay, so absolutely have to begin by crediting the guys who did all the work here. Now, on the right, Howard Stone will need no introduction to you. Phil Trin you may not have come across before, but you will do, because he's a very bright young mathematician and scientist, and he's going to be a big star in the future. So it's been a pleasure to spend a bit of time with him. When I first got to know him, it was when he was in Princeton, when I was on leave there. He's now back in Oxford, and so I've had the chance to carry on that collaboration with him nearer to home. So Phil Trin, watch out for him, very, very bright young mathematician, doing many interesting things. This is just one little part of what he's been up to. Okay, so what am I going to tell you about? I'm going to tell you about a very simple problem of a plate, elastic or rigid plate, on the surface of a viscous film. Very simple problem. There's several reasons you might be interested in this problem, and I'll try and sketch those for you on the next couple of slides. But actually the first time I ever came across it was as a very simple model for a contact lens, the kind of contact lens some of us use. It's a very bad model for a contact lens, highly idealized model for a contact lens. But and it was written and published as a paper back in the late 90s by Moriarty and Terrell that formulated the model and did some of the analysis of it. Really nice problem, kind of got forgotten about a little bit. With the advent of some of the things that are going on at the moment in microfluidics and such like, there's been a bit more interest in these kind of things, and it's reinvigorated our interest, in particular in that paper, but in problems of this kind in general. Okay, so I claim that whether or not you care about contact lenses, this is an interesting problem. Because it's a sort of very simple paradigm for a fluid structure, a non-trivial fluid structure interaction problem that you stand some chance of being able to do without having to just do massive computation. Actually, why did we get interested in this? Well, we got interested in it because people were doing flexible blade coating problems, and this is a picture of that here. So we're all, I guess, familiar with standard blade coating, where you have some liquid, you have a substrate of some kind of blade, and as you drag the blade over the substrate or the substrate under the blade, you pull liquid through, and you end up with a liquid here somehow on the substrate. That's kind of what a blade coater, a coater of any kind, does. There are lots of coaters out there, lots of designs, lots of work's been done on them, but relatively little on a situation where the blade itself is very flexible. So there's various papers come out recently. This is just one I've mentioned here, but there's quite a lot of work in different places going on this. And it's an interesting problem to try and understand how the properties of the blade interact with all the properties of the fluid, and in the end, what you end up with on the left-hand side here. So what you'd really be interested in is blade coating The problem I'm going to solve for you isn't quite that, but it has elements of it, and it's hopefully a step towards understanding these kind of problems. I mean, I should just as an aside say, this kind of problem, once you see it, it comes up all over the place. I was in Oxford on Friday. I went to in fact, Andreas here was there as well. We went to a really nice presentation by Tom Wittelski on toothbrushing. Okay, so it turns out that the way toothbrushes work, the toothbrush you all use every day, is rather like this, and it all comes down to what happens to the toothpaste and how the particles of toothpaste are trapped under the blade. Is that right? It was all this kind of stuff some of it was this kind of stuff he was talking about. So this apparently, though I didn't know it when I wrote these slides, it also has an application to toothbrushing, so that's got to be important. Okay, right, but fleetingly to contact lenses. Now, so look, I do not claim that this is a good model for a contact lens, but historically that's where the mathematicians first got interested in it, so I kind of feel I have to put at least one slide with some contact lenses on it. Real contact lenses are very complicated, so this rather bad picture taken from this paper tries to show some of the things that go on during a blink. Here's the eyelids, here's the lens, here's various other things. Here's the eyelid going across and then sweeping back. And so there's all sorts of interesting questions, mechanical questions, biological questions here. One thing this is definitely not is a rigid plate moving constant speed across a flat substrate, which is the model Moriarty and Terrell used. But you can kind of see it's got some of the features of that, and certainly if you want to understand this problem, you would want to understand what's going on with the tear film, what's going on with the lens as it sweeps over the top, all sorts of interesting things there. The permeability of the lens can be really important. I'm not going to talk about any of those issues. I just want to make clear that real contact lenses are much more complicated. But what I'm going to tell you might have some small relevance to the real physical problem. And that's what I just said, right? So there's lots of work, hundreds of papers, thousands of papers on contact lenses to do with forces, to do with rupture, to do with blinks, to do with dry out of the eye and such like. What I'm going to focus on here is this kind of toy problem, and the feature that I think is important in what we did is to worry about what's going on with the capillary forces, what's going on with the liquid either side at the two ends of the lens. I'll draw you a picture of that in a second. And as I say, the place where we got into this was this paper by Moriarty and Terrell, where they wrote down a nice simple mathematical model to capture some of that. And I should say that this paper is in EJAM, European Journal of Applied Mathematics. There is a follow-up paper. In fact, it's the next paper in the same issue by Bryce McLeod, a very famous name, of course, known to many of you. And what he did in that paper was he did try a more mathematical approach to the problem and proved various things that mathematicians want to prove about problems in terms of the existence and uniqueness of solutions. So if you ever do get interested in this problem, maybe you want to look at that paper, do make sure you look at the next paper because it's got some interesting insights in it as well. Okay, so I'm not going to talk about that paper, I'm just going to talk about the original Moriarty and Terrell paper. So here it is. You can see it was setting out its stall from the start, that this was about contact lenses. And actually, here you can see the abstract. It talks about all sorts of things. It talks about pressure, it talks about surface tension, it talks about quasi-steady motion, and in particular it talks about both 2- and 3-dimensional problems. So there's a lot. It's quite a short paper, but there's a lot in it, and I'm going to tell you a little bit about a few of them now. So this is the problem they actually studied. Horizontal lens, rigid plate, on a horizontal substrate, one moving relative to the other. They had their substrate moving to the right, and they're interested in what's going on underneath the lens, and they're interested in what's going upstream and downstream of the lens. So there's a free surface upstream of the lens, there's a free surface downstream of the lens, and what makes this a fun problem is in general all of the things I've just mentioned are all coupled to each other. So you won't know about what the lens is doing unless you know what the liquid's doing, and of course the liquid has got a free surface, so you've got to find out what the free surface is doing as well. So that's why it's an interesting coupled solid fluid structure interaction problem. Okay, so what did they do? They formulated the problem. I'll do that for you myself in a moment. And there's a couple of parameters. The obvious one here is the height of the lens. And then there's also a capillary number that's effectively a measure of the strength of surface tension. And then depending on the values of those two parameters, they found out that the problem might have, well, it might not have any solutions at all, but it could have as many as 2. Later on, we put in some gravity, and actually that turned out the answer could be as many as 3 solutions. But that's not really the point. The main point of what they did was very sensible. They looked at this case of a flat lens, which definitely made sense as a first problem, but they didn't write down the full problem, and in particular, the solutions they obtained are not in general equilibrium solutions of the whole problem. So they didn't let the lens tilt, they didn't let the lens move up and down, they just said, well, okay, it's fixed at a given height. There's no guarantee in their formulation that actually it's an equilibrium solution of the full problem. So what we thought we should do is take the full problem, look at the whole problem, and go back and then see, basically reassess what they did with a little bit more care. And in fact, it turns out that a lot of what they said was very good. So this is not... we came away from this with increased respect for what they've done, not less. Okay, so actually I'm going to talk about two problems because they're sort of similar but kind of different. So here they are. So first one I'm going to call the pinned problem. Now this is not pinned. I was using the word pinned earlier in the talk. This is completely different. So the first problem I'm going to tell you about, well, so let me say the second problem I'm going to tell you about is effectively the contact lens problem I've just been describing to you. So it's horizontal substrate, a lens now, however, that's free to tilt and free to move up and down. Remember, Moriarty and Terrell just kept the lens fixed flat at a certain height. So that's kind of the problem we started off talking about. I'm going to call that the free problem. But kind of as a warm-up for that, I'm going to tackle a slightly easier problem, which I'm going to call the pinned problem, and that's kind of the same. I've got a blade that's allowed to move, I've got a free surface, but I'm going to pin this upstream end of the blade, and I don't, in that case, worry about what's going on upstream. So there's no upstream free surface, just a downstream one. The blade isn't completely free to move, it can't move up and down bodily, but it's pinned here, and so it can tilt up and down. And that's kind of a halfway house towards the free problem, but it also looks a lot like that flexible blade coater problem that I was telling you about 10 minutes ago. So the hope is that somewhere between these we can understand what's going on. It turns out once you've understood this one, it isn't much harder to understand this one. It turns out actually this one's got slightly more interesting, in some sense, behaviour than this one. It turns out they're both worth spending a few minutes talking about.
Sorry,
Question, yeah.
Very stupid question, but in the free problem, what keeps the plate from moving?
So it might be the weight of the plate, for the inertia of the plate, for example. But that's a very good question. Yes, I'm going to say a word or two about that. You're right. Although if it was just as I've described it to you with nothing else, it would simply get swept away downstream. Whereas that's obviously not an issue for the pinball. Okay. So let's formulate a problem. Let's try and make it as easy as I possibly can get away with. So I'm going to just use Navier-Stokes mass conservation, and I'm just going to assume everything's thin, so I'm going to use a lubrication approximation. I'm going to have the lubrication equations that we all know about, and I'm going to remember that for a steady flow, and I'm only going to just think about steady flows most of the time, that means the flux of fluid under the blade and under the free surface are the same and are constant. Okay, so under the free surface, it's a classic thin film free surface problem, and any one of you who've ever done those kind of problems know that within a couple of steps you get immediately to a very famous evolution, ODE for the shape of the free surface, and here it is. It's usually called the Landau-Levitch equation, and it's a third order equation for the shape of the free surface. Q is the flux, which is a constant, and delta here, well, delta is my inverse capillary number, so you can think of delta as non-dimensionalized surface tension. Okay, so that's a very, people who've done this before, if you have, that'll all be very familiar. If you haven't seen that before, don't worry, it's an ODE for the shape of the free surface. Okay. So what's going under the plate is completely straightforward. What's going under the free surface is completely straightforward and standard. But what makes this fun problem, why I'm spending some of your valuable time this morning telling you about it, is the fact that these two problems are coupled to each other. And that turns out to be quite fun. Okay, so I need to say what kind of plate I'm telling you about. And I guess I could take anything, but just to keep things relatively simple, I'm just going to take a flat plate. But I don't want it to be too boring, I don't want it to be horizontal, so I want it to be able to move up and down and to tilt. So I'm going to look for a plate, I'm going to use a plate that's a linear function of x, where in general I won't know either the height at the origin or this slope. So depending on the problem I'm doing, one or both of those are going to be unknowns. Okay, so let's do those two problems. I'll do the pinned one first, then I'll tell you about the free one, then I'll finish off with some conclusions. So here's that picture again. So we're going to look at the pinned problem. Now it turns out one of the things you need to understand this problem is to be really clear about what the knowns and the unknowns are in each of the two problems. They're not quite the same, and at the start when we were doing this we got rather confused because we weren't always quite sure. Well, counting up your unknowns and equations turned out to be slightly non-trivial. Okay, so what are the knowns? Let's look at this pin problem. For the knowns, for the pin problem, we're pinning the plate here, so this height here is a known, right? And we're going to non-dimensionalise things so that that's 1. The other known is we're going to say we know the pressure up here. We're going to call that P0. We can play with that. That's an input parameter. So those are the two knowns. What about the unknowns? Well, of course, we don't know the angle of the plate. That's going to tilt to take up the position it chooses. So alpha is an unknown. And the other unknown in a problem like this is you don't at the start know how much fluid is going to go through underneath, and so you don't at the start know what the downstream height is going to be. So for this problem, the unknowns are alpha, that angle there, and h infinity, the height down here downstream. Okay, just bear that in mind as we go forward. Okay, right. So now we've got the solution. We've got flow under the blade. We've got flow under the free surface. We have to join all those together to make sense of it and to make it the full coupled problem. So I'm just going to write down the crucial conditions. So the first thing we have to do is we have to join up the pressures. So the pressure at the end of the blade has to be the same as the pressure under the free surface. Here's the pressure from the flow under the blade. Here's the pressure from the flow under the free surface. You'll recognise this. This is a second order derivative. This is the usual capillary surface tension, curvature surface tension term that you always come across in any free surface problem of this kind. You can write down what the pressure under the blade is, and so you get some sort of equation looking something like that. The details aren't particularly important. I just want to give you a feel for the kind of equations we're dealing with here. Right. Crucially now for this problem, what we need to do is we need to write down the condition of zero moment on the plate. We're not interested in a force balance on the plate because it's pinned, but what the plate's going to do is it's going to take the position that it chooses such that it's got zero moment, in particular such that it's got zero moment about the pivot. So here is the moment, this is the moment of the pressure, kind of makes sense, there's an x, there's a p, here's an integral, and here perhaps this term may be a bit less obvious, that's the moment of the surface tension force pulling at the end. So here's the plate, pinned at one end, moving up and down, there's the pressure from the fluid underneath the blade, pushing up and down, that's got a moment, a net moment on the pivot, but at the end we've got surface tension forces pulling on the end of the plate, and that force there pulling at the end, that also has a moment, and that's what that second term there is. Okay, so what we've written down there is no net moment on the plate. Again, you can write these things down, there are some functions there that you can work out because you're doing it's all in a lubrication approximation. So those are details, but the point is no moment. Okay, so you can compute that problem. It's not straightforward, but if you're as clever as Phil is, you can do it. Before we do that, let's just think a little bit about some limits. So the obvious limits to play with are large and small delta. So small delta, that's weak surface tension, or alternatively very fast motion, right? The equivalent. Okay, so in that case, it turns out that what happens is the plate takes up some angle that we're going to be able to write down, and there's some region at the end of the plate where things adjust, but we don't need to worry about that. And so actually you can write down a simple expression for the height of the free surface and an equation that will give you the plate angle. You're not going to be able to see anything from those, so here's a picture of it. So this is the plate angle as a function of the pressure, and I've just drawn a picture of something you can calculate exactly. So what do you take away from this picture? Well, what you take away from this picture is if the pressure is negative, if you're sucking at the left-hand end, then there's one solution, and the angle is negative. What does that mean? So here's the plate, sorry, I'll try and do it from your perspective. Here's the blade going up and down, so positive angle like that, negative angle like that. So a negative angle corresponds to the plate coming down close to the plate. An angle going to -1 in the way I've scaled it corresponds to the blade coming right down and very, very close to touching the plate. So as this angle here is asymptotic to -1, the blade is coming closer and closer and closer to touching the plate. So what you've got there is you've got a situation where you're sucking the blade down onto the plate. Okay, positive pressures, you can have two solutions. one with a small angle, right, so these are positive, so one angle or another angle, you can have two solutions, and as you keep on increasing the pressure, that can actually eventually, those solutions merge. And for a larger than a magic value, 1 and a bit in this scaling, no solutions at all. There's a solution here with the angle going to 0, that's becoming flat like this. There's a solution here with, as the pressure goes to 0, the blade angle going off to infinity. Right, that's not physical, this is a lubrication approximation. What that really means, of course, is that the blade angle's getting large. Okay, so that's exactly what's happening when surface tension is weak. What about when surface tension is strong? Well, you can kind of guess what's going to happen in that case. Surface tension is strong, surface tension is pulling out really strongly in both directions, and what you end up with is the plate is flat, and the surface tension, the free surface, is pulling out almost horizontally at either side. So everything's fairly boring and flat all at the same level. That's exactly what the math tells you. So the math says the angle is small, in other words, the blade's almost flat. The free surface is almost, the height at infinity is 1, the height of the blade is 1, it's all basically all lined up at height 1, and then the differences are all small, right? Delta's big, so these are all small corrections. And it kind of has the obvious shape. There's something slightly interesting there. There's a 6 that makes a special, yeah. So why is 6 special, right? Because here the sign of alpha depends on whether P0 is bigger or less than 6. Well, that depends on whether there's a net positive or negative pressure gradient under the plate. But if there is a positive one, it tends to go slightly up. If there's a negative one, it tends to go slightly up. Okay, right, that's the limits. What about the general case? Well, this is the numerical computations. I'm sorry, I've switched now to the height at infinity as a function of the pressure rather than the angle, but you see the same features. So the dotted curve here is the asymptotic curve, showing the two solutions and then no solutions. So that's the asymptotic solution for small delta. The other curves here are numerical solutions for larger values of delta, in other words, stronger values of the surface tension. And what you can see happening is this curve unwrapping, opening out. For a small region here, there's actually a triple valued curve here, an S-shaped curve with potentially as many as 3 solutions. And if you keep making the surface tension stronger and stronger, this curve gets pulled right out, and you end up, for large enough values of delta, with a unique solution for all values of the pressure. So you go from 2 solutions or none through a small region of 3, and eventually you end up with 1 solution for any value of the pressure. Yes?
Does the transition exactly happen? What happens to the curve when?
I think, from memory, there's a curve. This transition here, these two merge and you end up with a vertical slope here. What happens here? Well, it's quite hard to know. It's difficult to do the computation up here. So we know what the form of the curve here is for small delta. It blows up exponentially. So presumably what happens is, for a small but non-infinitesimally small delta, that curve just starts to curl. So it curls round and is asymptotic over in that direction. So it becomes S-shaped immediately, I guess. And it's not S-shaped in the limit of small delta.
Could there be a second branch?
Yeah, I mean, this is so yes. You know, doing the computations up high here was difficult. Doing the computations at all was quite difficult. This was the biggest range. I mean, so I wouldn't swear to understand. It could be. Now, this picture is correct. You know, I believe this picture to be accurate, but this is, in general, these are just numerical calculations. So, yeah, I mean, I know about the extremes, but in the middle, it's not quite so clear.
Could you say something about the inset?
Yes. So sorry, I didn't. So the inset is a physical picture of what the system looks like. So here we've got a situation. So we've got a situation here where we've got the blade. So ignore the dot there. The height here is 1, so it's pinned at this end here. This is a solution, physical solution with quite a large contact angle, a large blade angle. Here, the free surface drops quite rapidly. The free surface out downstream is almost flat. So the height at infinity here is kind of about 2 or something like that, 2 roughly in those units. The blade angle is there. And this is the physical solution at that point there. That's what the dot means.
Are these patches?
Right, yeah, sorry, not very clear perhaps. So the patches are showing the velocity profiles underneath the blade. So out to the, so these are velocity profiles drawn in this direction. So out to the right, where the free surface becomes flat, you essentially have uniform flow, like a rigid body translation. The fluid becomes stationary, it's just moving with the plate. So here is that rigid body velocity. It just looks like a straight line because it is effectively. Under the blade, of course, the flow is more interesting. Here you've got a parabolic, well, you've got a combination of shear and Poisson components. So here you've got a velocity profile of this shape. Here, where the blade gets wider, you get some backflow near the top of the blade, also here, and the velocity is 0 on the blade. In fact, so it's not quite backflow, but it will be if I went a little bit further to the right. So the velocity here is low at the top, and of course always, the fluid's always being dragged along with speed 1, so the velocity is always 1 on the plate. Okay, sorry, I should have said what that was, yes. So that's a physical sketch. I've got a few more of those coming up. So these are the kind of, so that's a bigger version of the same kind of picture. The colours haven't come out brilliantly. In fact, the colours have come out rather weirdly. Again, you can see, if you look, the velocity profiles. Here's the blade. Here's a solution with a relatively large angle. This is a solution below that critical pressure where there are 2 solutions, and here's the other one with negative angle. Okay.
Sorry, I was confused about surface tension in the one before, because corners like that.
It's not quite, well,
Surface tension.
so surface tension is very much in this problem. This is a situation with relatively weak surface tension, but remember, this is a long, really long and thin, and it's been drawn rather short and fat. So this is drawn as if it was all order 1, but it's long. It's a thin film analysis, and everything's been scaled. They've been scaled differently in 2 directions. So really, physically, you need to squash it down to make it look longer and thinner. But no, that's what happens in the limit. In the limit of small surface tension, the asymptotics tell you you've got a solution where the flat film out here is flat. This blade is doing its thing here, and there is a thin region, a boundary layer region near the end of the blade where it makes a rapid adjustment. So yes, no, it should be a region of rapid adjustment in the limit of small surface tension. I guess that kind of makes sense, right? If there was no surface
as long as the
tension.
surface tension is
Yeah,
very
so
small,
this is a relatively
Yeah.
weak. The delta in this problem is relatively small. Okay, there's the other one. And as you keep going out to the right, as you start, here's a situation where everything's getting fairly flat and a bit more boring, like I mentioned to you earlier. Here's a situation with a larger pressure, and this is, you're now in the regime where you're past the right-hand side of the nose of that picture, where you've just got one solution, a fairly sort of straightforward solution with a blade tilted down and a free surface just going out monotonically to infinity. Okay. There's not a great deal more to say about the free problem, because it turns out once you've understood the pinned one, the free one comes along relatively in the same kind of way. So let's quickly just go through the same ideas for the free problem. So again, we need to just be clear about what we know and what we don't know. So in this case, what we know is we would know, or we can imagine a problem where we know the height of the film out at infinity. So we've got a film of liquid, and we put the blade on top of it, but what we won't know is the height or the angle of the blade. So we don't know what height it's at, and we don't know what orientation it's at. So in this case, the unknowns are h naught and alpha. H infinity, in this case, we would know. Same kind of idea, just briefly, we've got to make everything join up. We've got to ensure that the things are continuous, not only now at the end of the blade like before, but at the front and the back of the blade. So you've got to write down continuity pressure at the front, continuity pressure at the back. We get something that looks like. I just put this equation up because I quite like this, because in some sense this encapsulates why this is a fun problem, because this is a nice condition that couples the free surface downstream of the blade, curvature of the free surface downstream of the blade, the curvature of the free surface upstream of the blade. That's the difference in the surface tension forces pulling at the two ends of the blade, and they're coupled together via the flow under the blade. And that's kind of all encapsulated in that nice simple equation. Okay, this thing can move, so we need to write down a vertical force balance on it now, and that's what I've done there. Here's the force, the integral of the pressure, and here, again, rather like we saw before with the moment, here's the forces pulling on the ends of the blade. So that's the vertical force balance. I also, as before, need to write down a moment balance. It doesn't now just have to be about the pivot, because there isn't a pivot. It's got to have zero moment about all points on the blade. And so you'd end up with some kind of equation like this, a moment of the pressure, and again a contribution from the moment of the forces pulling at the ends. Okay, again, just quickly, surface tension is weak. What happens in the case when the surface tension is weak is what you have is a solution where the film is basically flat and the blade is basically flat. But if you think about what happens under the blade, you go from a solution for a flow with a free surface for a solution with flow with a rigid surface. So they can't have the same flux if they've got the same height. And so if you think about it, what happens is the free surface flow is at one height and the height of the blade has to be at double that height to conserve mass. So if the height out at infinity is 1, because I've non-dimensionalized it that way, it means the height of the blade has to be 2. So here's the substrate down here, here's the flat film if nothing else had been going on, and the blade sits at twice that height, but it sits flat in this limit, right? So there's a situation where that Moriarty and Terrell solution is working out. There are regions near the end again where the surface tension sorts things out, but at leading order, we don't need to worry about those. Surface tension is strong. Well, again, everything just gets pulled out flat. So it's fairly boring. You just have a flat blade sitting in a flat free surface. The nice thing about this problem is you can actually work it all out asymptotically, so you can work out all the corrections. So if you've ever done one of these problems with a drag-out problem or a Landau-Levitch problem or a Bretherton bubble or all these kind of problems that look a bit like this, you can do these kind of asymptotics, but you can never quite join the whole thing up. What's cute about this problem is you can actually complete everything. Not only can you see that it's got monotonic decay one side of the blade, it's got oscillations the other side of the blade, but you can even match it all together and work out the phase shift. So kind of nice that it all comes out, but in the end it's what you're sort of expecting. Here's what these look like. Here's a solution with a relatively large angle. So here's the downstream film, here's the upstream film. You can see that's a little bit more wiggly. Here's a solution that's definitely not got a flat blade. And as I increase the this is relatively small surface tension. So if I'd been even smaller, it would have been sitting up at height 2. Here's height 2. It would have been sitting up flat at height 2. As I start to turn up the surface tension, the blade starts to tilt. The blade starts to tilt, and as I make the surface tension stronger and stronger, I end up eventually in the limit, with it pulled out almost flat. And if I'd gone to even larger surface tensions here, I would have ended up with a flat blade with a flat free surface. So actually this is a bit less interesting in a sense than the pinned problem, because for this problem there is always a single unique solution, and essentially it really always just looks like this. It starts off at height 2, and as I turn up the surface tension, it gets pulled down flat. There's no multiple solutions as far as we can tell in this free problem. Okay, so I started off with this paper. I want to finish off with it. So in general, they didn't write down force and moment conditions, but having said that, what they did, you do indeed recover their solutions of the flat blade in the extremes. So when surface tension is strong, you get a flat blade. When surface tension is weak, you get a flat blade. But in the middle, when it's order 1, you don't. And those are the solutions I was just showing you. Okay, so I am done. It took longer than I hoped, but I'm going to finish ahead of time just. So pin problem, there can be various potential possibilities for the solutions. For the free problem, there's always a unique solution. I just told you about the Moriarty and Terrell solutions. They apply in the limits, but not in general. And what we really wanted to do, of course, was the elastic version of this problem. And so my last slide is just a preliminary couple of pictures of the corresponding problem when the blade is elastic. So now it's a little bit trickier because you now have to solve, of course, for not just the position but the shape of the blade as well with some suitable elastic model. We just took a really simple one. And in the limit of a stiff blade, you should go back to the rigid case I've just been telling you about. Actually, as far as the current state of play is, we're sort of getting there with this, but the floppy limit, the weak elasticity limit, is quite tricky. These are the kind of things you get as you play with, in this case, you're playing with the stiffness. So that's a relatively floppy blade, and that's a relatively stiff blade. That looks more like the solutions we've just seen. Okay, lots more to do. This is all 2D. You've been interested in 3D. Of course, the real eyeball is much more complicated. And more generally, there are a whole variety of fluid structure interaction problems of this general type that people are getting interested in microfluidics, for example, where you have, I'll talk to you about that if you're interested, but there's interest in these kind of problems in a microfluidic context. Quick thank you, where I spent a bit of the time doing this. And I thank you very much for your attention. I hope I've not overstayed my welcome too much. Thank you very much.
What is going in microfluidics?
So, so I'm not the world expert on microfluidics at all, but in Howard Stone's lab, they're doing all sorts of interesting small-scale flows, and a variety, quite a few of those, they've got rods or fibres of some kind that they're trying to either join or keep apart with fluid dynamics. So there is one problem that he's quite interested in at the moment, where they have a kind of an array of like bristles, not quite bristles, but a bit like a brush. Very small scale array, and they want to know what's happening. Are these getting pulled together into clumps by the action of the fluid, the capillary forces, or are they getting pulled apart? And there's a whole interesting dynamical system there going on with these bristles. I call them not really bristles, but these plates getting pulled together into clumps and then moving as clumps and breaking apart. So there's a really complicated set of problems there. But one basic problem is if you just have two fibres with fluid in between them, and how they can be pulled together or pulled apart by the action of the fluid between them. There's some nice work that Howard and co-workers have done in the last 2 or 3 years about even just two fibres with fluid in between and how they get pulled or opened up, all motivated by some of these small-scale microfluidic applications.
You're talking about steady-state solution. Can you get some oscillatory behaviors here?
So yes, so this is something we're quite interested in at the moment. In fact, so I've been talking to people about this recently, about looking at some of the unsteady versions, even just simple versions of this problem. I mean, look, in a sense I can say we've already done part of it, because if you take a sequence of solutions like this, you can interpret those as a quasi-steady evolution. Of the unsteady system. Of course, that's cheating, really, because they're really just the steady states. Yes, so we've had some very preliminary thoughts on how you do unsteady versions of this, but I think there's a lot of that still open, interesting stuff that's there to do. Yeah, I mean, even just a simple problem like a wedge, a closing wedge, for example. How does that close? Certainly, if you have a situation like that, you can get oscillatory behaviour.
Can you get it because you have two stable solutions?
So that would be very interesting, wouldn't it? So, for example, in the situation, the pinned case I was talking about here, where there are two steady states, you would hypothesize probably of the two that the one with the big angle was likely to be unstable. For the simpler fixed blade coater problem, where we found there were as many as 3 solutions, we did actually run unsteady calculations for that. And in the case when there were 3, so not this problem, the case with a flat blade with gravity, there were 3 potential steady state solutions. We did run unsteady calculations and found what we guessed that of the 3, the middle one was the unstable one, and the lower one had by far the least energy. So, numerical evidence suggested that the lowest one was the stable one. It would be fantastic to do that for some of these problems here. We haven't done that for this problem, but in principle we could. So there's plenty more to do.
You had this one plot, I think, in the low surface tension limit, plotted over pressure, where you had 2 solutions at
Yes.
small values and no solution at large values. What would happen at?
Well, exactly. So that would
be a time-dependent state, right?
So in the very simplest situation of this limit here, that's exactly what you're just saying. So what could happen? Yeah, you could go to you could get an unsteady behaviour here. You could get. I mean, we did do a problem different to this years ago with the blowing on a drop, where we ended up with very similar kinds of behaviour. And there, one way of getting past the nose, if you like, was just change the topology. So in the case of a drop, the problem we were doing then, the drop could split. And there you had a very similar kind of diagram, but you had a whole variety of solutions with different topologies breaking off from the nose. It's a little bit like the pinning problem I started off with. The basic solution lets you down. What happens instead? It could be unsteady, it could fall off the cylinder, or it could just change somehow. In the case I started off talking about, it depinned. I can't quite imagine what the corresponding thing is here. So I assume it's going to be unsteady. Okay.
Okay. Any other questions? Let's